Let's recap what the bag of words model is doing. What we first decided to do is we decide what is going to count as a document for our analysis. In this case, we decide that each sentence is going to be a document. And what the bag of words model does is going to take each document, it's going to break it down into words, and it proceeds to count the number of times the words appear for each document. Tokenization refers to dividing up a document into pieces to be counted. So far, we've broken down the document into words to be counted. But we don't have to break it down into words to be counted. Perhaps we want to count something else besides words. Maybe we want to count the type of punctuation that sentence uses, or the punctuations that exist in the document. Tokenization, so tokens, when we say tokens, that simply is going to refer to what we are counting in this bag of words model. Now I want to say that the term frequency inverse document frequency isn't strictly the bag of words model, but in some ways it's just a modification of the bag of words model. It still relies on generating a count matrix, and it's just going to adjust the weights, adjust the counts for the resulting matrix. But nonetheless, it's simply a counting process. We don't have to count just words. In fact, let's consider a sequence of two words. In our current approach, if we have a phrase like natural environment, we would count natural and we would count environment. But we wouldn't be counting the occurrences of that sequence, natural environment. We could extend what our tokens are from just simple words to what are called bigrams. So in other words, a bigram is just a sequence of two words, like natural environment. And this is important because by adding bigrams, what do you think we're doing to the model? What do you think we are doing to potentially improve our model's performance, boost the signal in the data set? What do you guys think is happening if we include bigrams, if we are counting bigrams as opposed to just words? In this bag of words model approach, each word is a feature. So if we are now counting bigrams, we're going to increase the number of features for our model to use. So increase the dimensional space. So hopefully that's going to inject more patterns, more behaviors that our machine learning model can use to exploit to make predictions. And let's go and examine an example of bigrams. I mentioned one, natural environment. And this is important because a word like environment might appear at a relatively same frequency across our corpus. For documents referring to Python, the programming language, and Python, the animal, it would make sense that we'd see environment at relatively the same frequency. So perhaps our model wouldn't be able to exploit the frequency of environment to make a classification. But what about the bigram natural environment or virtual environment? I would argue if we look at the documents that compose our corpus, we'd see that virtual environment, when it does appear, it's going to appear mostly in documents referring to Python, the programming language. Same thing with natural environment, but with respect to Python, the animal. So you can see now if we counted natural environment and virtual environment, including this bigram as a feature for our analysis, potentially will boost the signal in our data and help out our machine learning model downstream. In general, we can say n-grams, so any n sequence of words. So we can go ahead and do trigrams and quadgrams and whatever higher number of grams. But what do you think would be the consequence if we go a little too crazy on the number of n-grams we use for our analysis? In other words, we're going to count words, we're going to count bigrams, and let's include trigrams. Any consequence of including trigrams and higher number of grams in our analysis? As we increase the number of grams we want to include in our analysis, we're going to increase our feature space dramatically. That's going to be a problem because we're going to have a larger data set, so it's going to be harder to train. We have too many features, so we might have issues with overfitting, and now there's so many different types of tokens that we have to count. And that's going to really slow down the counting process, the upstream part as well as the downstream part with training our model. So typically when people do n-gram analysis, they rarely go beyond bigrams. So let's see how we can go ahead and use our tools in scikit-learn to include bigrams or n-grams in our analysis. This can be done by changing the keyword argument n-gram range for our transformers, our bag of words transformers. To look at the n-gram range, we need to pass it a tuple. A tuple that says, okay, what are the n-grams to include? So we have to give a min n and a max n. In other words, if we only wanted to include words as our tokens, only count words, then our n-gram range is going to be a tuple of 1 and 1. In other words, start from 1 and don't go beyond 1. If we want to include bigrams and unigrams, or just simple words, as our tokens, then we go ahead and set the n-gram range to go from 1 and 2. So we pass it a tuple of 1 and 2. We could also only count bigrams. And if we only wanted to count bigrams in our model, we'd simply just pass the tuple 2 and 2. So let's play around with counting bigrams in our model. So I'm going to go back to the count vectorizer. In this case, I'm going to set max features to 20. I only want to look at the top 20 bigrams, which bigrams have the highest occurrence in our corpus. I only want to count bigrams, so the n-gram range is set at 2 and 2. Let's include stop words. And let's see what happens when I look for just counting my bigrams. So I did that. I'm going to get the get features name. So it's going to report, it's going to give me a list of all the features, all the bigrams that I'm counting. So these are the top ones. I say 12 of September, which is interesting. Arbitrary precision, ball pythons, et al. Feet length, feet long. You can go ahead and look at look at the list. But yeah, so we see some common bigrams throughout our corpus. All right, so we answered this question here about is it practical to increase our n-gram range, but what about this question we have here? Is using stop words more important when we're using the count vectorizing hashing vectorizer or the TF-IDF vectorizers? What do you guys think? What do you think it would be more important to use or more crucial we use stop words? If we just simply have a simple count vectorizer, so just raw counts, or something where we're adjusting the weights of those counts, the values of those counts, through a term frequency inverse document frequency? What are your thoughts? Generally speaking, it's pretty cheap to include stop words or to incorporate stop words in our analysis. Remember, what stop words is doing is just preventing that word to be a feature. And we saw that with the TF-IDF vectorizer, we understand that words that are very common throughout our corpus, that have a high document frequency, those are going to have a very small inverse document frequency. So their counts might be high, might be present across all the documents, or majority of the documents, but their contribution will be weighted down. So stop words would typically be those words that would be weighted down. So I would argue that using something like the TF-IDF vectorizer would see less improvement if you include stop words, because it's going to naturally handle those stop words. But of course, we should always include the stop words. Why not? Yes, they'll be ideally the TF-IDF vectorizer would take care of them or will minimize those problems. But why even count them? Why include them in the analysis? So we'd see more of the improvement with if we had to use the count vectorizer, the hashing vectorizer. Those large counts will be completely omitted in our analysis. Let's consider document similarity. Sometimes we want to figure out what are some similar documents in our corpus. And let's go ahead and get a big picture of what we've done so far. We've taken text, unstructured data, And using something like the count vectorizers or the TF-IDF vectorizers, we essentially created a mathematical representation of each document in our corpus. In this mathematical representation of our documents, we can treat them as vectors in a high-dimensional space. And this is crucial that we view our documents as being vectors in space, because if they're vectors in space, then we can go ahead and analyze them as vectors, treat them as vectors, and see what are the consequence if we view them as vectors. And that was the whole goal of using these bag-of-words model, or the TF-IDF vectorizer. We get a mathematical representation of our documents in a structured format, rows and columns, a number of observations, number of features, so we can go ahead and use it for a machine learning model. So now the question is, can we look for similar documents in our corpus? And what should we do if we view them as vectors? So in other words, we have, and this is of course just a two-dimensional space, but we would have a large dimensional space. So we have a document that exists right here. And just draw the line there. And another document that exists right here. How should we express how similar these documents are? Let's focus on the direction. You can view that our documents are vectors are pointing in the direction of some idea, some concept, some general topic. So vectors that point in very similar directions will express very similar ideas and will be very similar. So given that, we understand that we want to measure, get a metric that's based upon the angle these two vectors form. And specifically, if we look at the cosine of that angle, we get a measure of the similarity of these two documents. If these two vectors are perfectly aligned, they form no angle in between them, so the cosine of 0 will be 1. Those two documents express a very similar concept, will be very similar to each other, express very similar concepts. On the other hand, if they form a 90-degree angle, then they're really pointing in different directions. If that's the case, then we can argue that there is no similarity between these documents. So we take the cosine of 90, and that was going to be 0, unsimilar documents. Now notice by using the cosine similarity metric, we're not considering the magnitude. We're not considering the magnitude of our vectors. We're just considering the angle between them. So we might have a situation in which we have two vectors, but they have different lengths. We have two vectors. Let's say this other vector here. It's a lot longer than this other vector. So if we were to use something like Euclidean distance and measure the distance between this point and this point, that's going to be a very large distance. So using Euclidean distance was not going to be great when we're looking at document similarity. Looking at the angle is not going to consider the length of our vectors. Now, do you think will we have a problem with different lengths of vectors of our points of our observations if we use something like the term frequency inverse document? We should not, because remember the term frequency is going to normalize the counts. But if we were simply doing raw counts, then we're going to have a problem with we're going to have documents at different lengths. So another way to express the cosine of the angle between them is simply the dot product. The dot product between our two vectors, and then we divide by the norms of the two vectors. So we get a score that's going to range from -1 to 1. Since we're dealing with counts, we're going to have always positive values, always non-negative values. So we're not going to have a cosine similarity value of less than 0, since we're just working with counts, or values that are based upon raw counts.